the recording. And Geoff, feel free to take it away.
Okay, awesome. Thanks very much, Sebastian. So yeah, this talk is called Life Without Pythons Would Be So Simple. And it's just going to be sort of a broad overview of sort of an ongoing set of research ideas I'm interested in, which I guess started with a paper last December with Hrant Garobian, Adam Brown, Lenny Suskind, not sure why I said them out of order, that was called The Python's Lunch, Geometric Obstructions to Decoding Hawking Radiation. And then there's a load of ongoing work in various directions with Netta Engelhardt and Arvind Shibadshib-Mokadan. So yeah, that is basically what I'm going to be talking about, but it is all really based on seminal earlier work from decades ago, actually, by Dessin-Exupéry. Always like to get that in there. Show some respect. Okay, so what is the sort of big idea of this talk? Well, ADS-CFT, we have this duality between dictionary, between things in the bulk and things in the boundary. And something that has been known for really quite a long time is that sort of seemingly simple bulk observables, like local bulk operators or whatever, can be dual to very, very complicated boundary observables. In fact, they can be dual to things that are exponentially complicated in the boundary, exponential in 1 over Newton's constant, exponential in n. So, you know, this is a feature of the dictionary that we've sort of learned to live with. It's a slightly problematic one, but it's one that exists. And the bulk observables that you know have this problem that are exponentially complicated are normally in the interior of black holes. So that's sort of one explanation for why they're exponentially complicated, is they're behind some sort of horizon. On the other hand, not all interior operators have a complicated dual. So for example, if we think about a one-sided black hole that's been allowed to evolve for a long time, say a large number of scrambling times, then the sort of infalling interior modes going to the black hole, even the sort of part of it that's inside the horizon, we can just evolve it back in time and it hits the boundary. And so that has some very simple reconstruction. On the other hand, sort of right-moving interior modes, the interior partners of the Hawking radiation modes, generally, you know, we think are very complicated operators on the CFT. They don't have any sort of nice, simple way to reconstruct them. So it seems like just being in the interior of a black hole is not a sort of sufficient condition to create this exponentially complicated dictionary. And there's also other subtleties that show up. So for example, some operators can be pretty simple to reconstruct if you sort of have access to the entire boundary Hilbert space, but can still be exponentially hard to reconstruct if you only have access to a sort of subregion of that Hilbert space, even if in principle that subregion encodes all the information about that operator. So for example, if we throw a Hayden-Preskel-Dary into an evaporating old black hole, then that ends up in the island of the Hawking radiation. And so in principle, it can be reconstructed from the Hawking radiation, but on very general grounds, we should think it should be exponentially hard to do so. On the other hand, if we have both the black hole and the Hawking radiation, we can just evolve backwards in time, coupling together, throwing the Hawking radiation back into the black hole, and the Dary will just move backwards in time and emerge out, hit the boundary. We can use the extrapolate dictionary to decode it. So the complexity of the bulk operator depends on the boundary degrees of freedom you have access to. Okay, so the big vision of this talk, and my claim is that we want to make some general rule to understand why some things are easy and some things are hard, and why some things are sometimes hard, sometimes easy, and that we have a very simple and general conjecture for what the answer to this is, and that's that. Have I got this the right way around? Yeah. I couldn't see behind the participants thing, that something is simple to reconstruct so long as it's not in what we call a Python's lunch. On the other hand, if it is in a Python's lunch, it's exponentially hard to reconstruct. Okay, so that's the sort of grand vision of the talk, that we can completely classify all sources of exponential complexity in the holographic dictionary. And honestly, most of what I have right now is that grand vision. All the technical details are still deep in the weeds of horrible GR calculations, which they will hopefully emerge sometime between the next week and the next decade. We think they're emerging. They seem a lot more emerged than they did a month or two ago. But a lot of them are still getting I's dotted and T's crossed. So yeah, my plan is just to sort of really lay out this bold vision, impress you all with grand plans, and you won't notice that none of the details are fully finished yet. Okay, and so just to add a bit more bones to this conjecture, it's worth noting that sometimes an observable can be in a Python's lunch with respect to sort of a subregion of a boundary, or like something like Hawking radiation, but not be in a Python's lunch with respect to the entire boundary Hilbert space. Okay, and this very naturally explains why something can be easy to reconstruct if you have access to all the global degrees of freedom, but hard if you only have a subsystem. Okay, so as I say, back in 2019, Adam, Hrant, Lenny, and I put out this paper that basically gave an argument based on sort of intuition from tensor networks, that any observable sitting in a Python's lunch should be hard to reconstruct. Okay, so a lot of the ongoing work with Netta and Arvin, though, as I say, there's various directions, is to try to argue the converse to that as well, which in many ways is a more radical thing, that these Python lunches are sort of the only source of this huge complexity. So I'm going to try and, most of the talk, maybe the first 2/3, going to be based on this more polished published work, and then we'll start getting into the speculative, still being worked out stuff. Okay, so let me start by explaining a sort of intuitive picture of what a Python's lunch is. It's pretty simple.
Can I quickly pause you, Geoff? Alex has a question.
Yeah, just a quick question. You're making it sound like there's hard vs simple, and is there not sort of a gradual level of how complex things are? For example, if something is like e to the x over log x, how would that compare?
Yeah, so argument is going to be that anything not in a Python's lunch is like polynomial complexity in G Newton, maybe just like order 1 of G Newton. It's basically the complexity of Hamiltonian, proportional complexity of like boundary Hamiltonian evolution. And then anything in a Python's lunch, we think, the conjecture is that it's proportional to something exponential in the size of the lunch, which I'll define later. So it's a precise conjecture for how complex it'd be. There certainly may be examples where the conjecture is wrong, but at least we'd hope that sort of generically they're true. Maybe there's weird oddities where, but gravity is pretty generic. Gravity really likes being generic, so it wouldn't surprise me if it's just always true. Okay, so what is a Python's lunch? It's very simple. Let's think about some sort of slice, a Cauchy slice through a space-time. And let's think first about a space-time that has two boundaries, right boundary and the left boundary. So here we have something that maybe looks like a slice through a thermal field double state, like an Einstein-Rosen bridge. And what you see is that as you go from left to right, it gets smaller, 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 has sort of a constriction in the middle, a narrow surface, which covariantly would be like an extremal surface. And then it gets bigger again as you go to the right boundary. Okay, so we say that has no lunch. On the other hand, you could have something more like this. And I apologize for the terrible hand-drawn diagrams that I was making late last night. So we have our right boundary, then it gets narrow, has a constriction, has sort of an extremal surface in space-time here. Then it gets big again, and that's the bulge, that's the lunch the Python has eaten. And then it gets smaller. Maybe this one is smaller than this one, or the other way around. There's some smallest constriction, and then it gets big again to the end. Okay. So that's just an intuitive picture to keep in your back of your mind as to what these things are. We'll define it all covariantly and so on later. But I also thought, so that's what you might think of as a two-sided version of Python's lunch. That would be the relevant thing if you're trying to say just reconstruct an operator from the right boundary. If you're trying to reconstruct an operator from sort of the entire Hilbert space, the thing you want to be thinking about is whether there's a one-sided Python's lunch. I've got a bit of background noise here. Is that coming through? Okay, hopefully it's okay.
It's barely there, but it's not a big
Okay.
issue.
Great. So for that case, the question is whether there's a one-sided Python's lunch. So basically, this might be sort of the ADS vacuum, or like just a one-sided black hole formed from collapse, and it just sort of as you go deeper into the bulk, the area gets smaller and smaller and smaller until it contracts to zero. On the other hand, this would be a one-sided lunch. It gets small, has some constriction with sort of a non-empty extremal surface for the entire boundary, and then it gets big again, you have some bulging lunch, and then finally it pinches off at the end. Okay. So that's the sort of two cases going to have showing up, but it's pretty easy to see that the one's sort of a special case from the other where one side is like trivial Hilbert space. Okay, but before we really start thinking about gravity, I want to think about a sort of simpler toy model where we can say a bit more about complexities of things, and that's going to be a tensor network. So what would a Python's lunch look like in a tensor network? Well, it's just a tensor network. All of these are tensors with things interacting, where it gets bigger. As you go from left to right, it gets bigger, and then it gets a bit smaller again. Okay, but it still ends up bigger on the right-hand side than the left-hand side, I'm going to assume, without loss of generality. Okay, so each of these tensors are either going to be, you can see there's some tensors where we have two inputs and two outputs. And in those cases, we're going to assume they're unitary. But we also have things where there's sort of one input and two output, or one input and two output going this way. And in that case, we're just going to assume that it's an isometry. So you can think of that as an ancilla qubit being put in the zero state, and then some unitary being applied. Okay. So assuming this tensor network is pretty random, then generically, just because the right-hand side has more qubits than the left-hand side, the entire network is going to be something very, very close to being an isometry when looked at as a map from the left-hand end to the right-hand end. On the other hand, because we have this bulge in the middle, if we look at the sort of individual steps, the individual sort of moving across from left to right, then not all of those are isometries, right? In particular, this bit where we go from the big bit here to a smaller bit, that's not actually an isometry. Instead, what's happening is that you have sort of two inputs here, and then one of them gets, one of the qubits or whatever gets post-selected onto being in the zero state. And so we have a linear map from 2 qubits to 1 qubit, which can never be an isometry. Okay, so let's say we have some bulk operator sitting somewhere in the middle of this lunch, and we want to apply some unitary operator in the right boundary that's going to change that bulk operator sitting in the middle. Okay, so the sort of naive thing we would do if there wasn't this lunch is that we just sort of start undoing the tensor network from the right-hand end, undo it, get to where we want, change it with our bulk unitary operator, and then redo everything all the way to the end. On the other hand, in this case, we can't just do that because there's no way to undo the map from here just to here because that map was not invertible. Okay, so if we want to change this thing sitting in here, the only way to do it is to apply a unitary that undoes this entire network all the way to here. Okay, because that actually was an isometry, that actually was a unitary, and then do another unitary that recreates the entire network with the adjustment made in the middle. Okay. Okay, so now we have the question, how hard is that to do? What is the complexity of fiddling about with the food in the lunch? Well, as a tensor network, this thing doesn't look too complicated, right? Like the complexity is proportional to the length of the lunch times the width of the lunch. That doesn't seem too bad. However, if we view it not as a tensor network, but as an isometry, then its complexity is defined in a different way. Its complexity is now not the number of simple tensors you need to construct it. It's the number of simple unitaries that you need to compose in a circuit, plus maybe adding in some ancilla qubits in order to construct this isometry from left to right. And it's very easy to see that these are just not the same, because the way the tensor network does this thing in a simple way is it uses these non-unitary steps. Okay, and so we want to replace them replace it by a product of simple unitaries, then we just need to construct the entire unitary in a totally different way. So let's just make that very explicit. So let's say we have some input state that I'm going to call ket I. Okay. This map to the output state that we'll call psi can be thought of in the following thing. We add in a load of, we add in a load of ancilla qubits in the 0 state when it gets bigger. We have some unitary evolution that describes the unitary evolution part of the tensor network. That's some pretty simple unitary because it's a simple network. And finally, we have all these load of qubits at the end that get post-selected on to make it smaller again. They get post-selected into the 0 state. That's a general description of this tensor network. And what we want instead is not this simple unitary U tensor network, because that also requires this non-unitary step. Instead, we just want some unitary acting on the whole thing without any post-selection that takes us from I plus some ancillas to psi plus some ancillas. Okay, so if we had that, then we can find a simple way to implement our bulk operator. Okay, so the question is whether this UPL, UPython's lunch, is a simple unitary or not, and if it's not, how complex is it? Another way to phrase that question is how hard is it to bypass this post-selection and convert this UTN plus post-selection into a UPython's lunch. Okay, so let's say you were trying to just prepare the state. This won't really work for what we want, but it will give us a hint of the right way to do this. Well, one thing you could do is you could just apply U tensor network and then measure all the ancilla qubits. Okay, and maybe you get really, really lucky and they all turn out to be in 0 state, and otherwise you just have to try again. Okay, well, how long is it going to take you to do that? The amount of time is going to be 2 to the number of qubits you're post-selecting on. So that's a really, really long time. And at the end of the day, it's not even a unitary process. You're doing measurements and stuff. But it gives you a hint that the thing we're trying to do is we're trying to search for all of those ancilla qubits being in the 0 state. And there's a way, a unitary way to search for a particular outcome in quantum mechanics, and it's called Grover search. Okay, so what is that? It's an algorithm that basically works in the following way. What we do is we first apply the U tensor network. We start with our input state plus ancillas. We apply U tensor network, and then we apply a phase of -1 if and only if all these like final qubits that we want to post-select on are all in the 0 state. So if we got lucky and got it right, it gets a phase of -1. But most of the amplitude is going to be in other states, and so they just stay the same. Now we apply the dagger of U tensor network. We evolve backwards in time. Okay, now of doing that, we apply a phase of -1 if all the initial input ancilla qubits are in the 0 state. Okay, if we hadn't applied the phase based on the output qubits, then this would just like always be true. But now there's going to be some amplitude. We're going to change the state slightly. There's going to be some amplitude for it not to be in that state. And so this is going to use something new. And then we're just going to repeat the cycle backwards and forwards. Turns out if you repeat this 2 to the number of post-selected qubits over 2 times a factor of pi or whatever, square root pi over 4, then it just slowly rotates the state around and it ends up giving you exactly the state you want on the output. So this is just a general way that we can always convert this U tensor network into a UPython's lunch, a sort of circuit for applying that the full tensor network unitary. On the other hand, this approach is still exponentially hard in the number of post-selected qubits. Okay, so that's just one way of trying to convert this thing into a unitary circuit. You could say, okay, maybe there's just a more efficient way. And maybe that's true. No one knows anything about complexity theory. It's way too hard. Maybe in a couple of 100 years, we'll all be good enough at maths and stuff to be able to answer it. But for the moment, we basically just have to assume conjectures and various things. But one thing that is known is that for black box search in quantum mechanics, then Grover search is optimal. So there's nothing that can beat it. Of course, in this case, it's not a black box search. We know in advance what we're wanting to post-select on. And so we could it's entirely possible that more efficient approaches exist. We can't rule that out. On the other hand, there's very strong reasons to think that at the very least, we can't end up doing it in polynomial time. And the reason for that is some formal computer science result that if you could implement and you simulate an arbitrary post-selection in polynomial time, then it would imply that BQP is equal to what's called post-BQP, which is a quantum computer that's allowed to cheat and do post-selection, and hence that it's equal to something called PP. It's a proof by Scott Aronson that post-BQP is equal to PP. PP is a classical complexity class, but it's a classical complexity class that's incredibly powerful, has an awful lot of stuff in it, lets you do incredibly powerful things. So this would mean that quantum computers are like way more powerful than you think. So yeah, you or I might say, sure, BQP could be equal to PQP. Who cares? That seems reasonable as anything. But if you suggest to Scott Aronson that that's the case, he will laugh at you. And honestly, proof by Scott Aronson laughing at you, proof by contradiction by Scott Aronson laughing at you when you suggest the possibility is about as rigorous as you can get in complexity theory at the current point in time. So we'll take that as pretty solid. Okay, so on those somewhat shaky but relatively solid as far as complexity theory goes grounds, we're naturally led to the following pretty reasonable conjecture, which is that the sort of unitary complexity of this Python's lunch tensor network is generically going to be proportional to the complexity of doing the Grover search, which is the product of two things. One is the complexity of just implementing the U tensor network itself, and the other is the number of steps you need to do in the Grover search, which is 2 to the post-selected qubits over 2. Okay. So that conjecture seems fairly reasonable. Computer scientists will still respect you for it. What they might less respect you for is the more speculative conjecture that we're going to make, that the same thing is true when we have something that looks like a Python's lunch in quantum gravity, ADS CFT or whatever. But we're going to make it anyway because we're physicists, so that's what we do. Okay. So having laid out a sort of general set of ideas about what a Python's lunch is, I now want to turn to the original example we were thinking about back in December that made us come up with this condition, which is evaporating black holes. So in particular, back in 2013, when everyone was obsessed about firewalls, unlike now when we just have discussion sections about them, then Dan Harlow and Patrick Hayden put out the following paper where they argued that to perform the AMPS experiment, i.e. to extract a purification of a late time Hawking quanta just out of the early radiation, which you can then jump in with and have a cloning paradox, is actually exponentially hard. And they argued this based on pretty general arguments about scrambling unitaries and assumptions about complexity theory and so on. From a sort of modern viewpoint with islands and so on, this is just the statement, the claim that in order to do entanglement wedge reconstruction of the interior partner of the Hawking mode, which is sitting in the island after the page time, that's exponentially hard. Okay. Very similar grounds. You can argue that sort of doing the Hayden-Preskel decoding of some diary that fell into the island, just using the radiation is also exponentially hard. Of course, as I said at the beginning of the talk, if you're allowed to have control of the black hole as well, then it's easy to reconstruct the diary in this case. So the question, which has an obvious answer given everything I said, is can this be explained by a Python slunge? Okay, so let's see what happens. For the moment, you're just going to pick a sort of slightly arbitrary, nice Cauchy slice that's going to sort of stick close to the event horizon. We're going to have this slice include the sort of quantum extremal surface, the non-empty quantum extremal surface, the island quantum extremal surface, and we will define everything more covariantly later. So very, very schematically, that Cauchy slice looks something like this. We have sort of the boundary out here to the right. We have a horizon. We have the interior of the black hole. And the wormhole is actually sort of narrowest at the horizon because the slice sticks close to the horizon. So as we go deeper into the black hole, it's going backwards in time. Black hole is evaporating, so that means it gets bigger. We also have these very schematic blue lines, which describe entanglement between these interior modes and the radiation that's off in some bath or whatever it might be. Okay, and by general arguments, going back to Engelhard and Wall, ER equals EPR, tensor networks, and so on, this bulk entanglement is sort of equivalent to a classical area. We should treat them on the same footing. So it's easy to see now, looking at this picture, that we have a Python slunge. We have two constrictions with a bulge in the middle. So as you sort of go from, you treat one end of the lunch is up here on the exterior of the black hole, one end in the Hawking radiation. You want to go through from left to right, it gets narrowest here, then it gets bigger again. Then at some point you can just cut through all these sort of micro wormholes that are the entanglement with the Hawking radiation, and that's a second constriction that's smaller again. Okay. And of course, the bulge in the middle, the bulge in the Python slunge is just the island. It's just another word for it. Okay, so we seemingly have a Python slunge. The sort of next question you'd want to ask is how big is this lunge? And the size you get when you do that depends on how you slice the lunch from one end to the other. But in order to sort of come up with the most efficient sort of Grover search protocol, we want to choose a way of slicing that minimizes that maximum size, to minimize the amount of post-selection, because that's really, really hard. So there are a couple of ways you could do that. One is you sort of start by creating a surface at the end of the wormhole and then gradually sweep it along until it's up here. So that works. And you can see the maximum size here is when we just created this new thing here. Maximum sort of generalized entropy is equivalent of sort of the size of the cut. There's an alternative option, which is you instead create a sort of double cut up here near the horizon and then sweep it along backwards. In this case, the maximum size happens just after you create this double cut, and it's now, instead of the entropy of the radiation plus the initial entropy of the black hole, the entropy of the radiation plus twice the final Bekenstein entropy of the black hole. Hence, this is more efficient than the I showed on the previous slide, when the black hole has more than half evaporated. It's important to note that more than half evaporated, like that transition where it becomes half evaporated by area is strictly after the page time, even though we often call the page time the point where it's half evaporated. So just after the island forms, then it's still more efficient to use this sort of forward sweeping along the wormhole. It's only later that this reverse one here becomes the most efficient thing to do. Okay. So what answer does this give for the complexity of say Hayden-Preskel? Well, converting it in tensor network conjecture into gravity language, we have the following formula. So we have first the complexity of the tensor network itself. That's going to be proportional to sort of the volume of the action. It's going to be proportional to total time. And then we have the sort of size of the lunch in there. Okay, so the size of the lunch is the difference between the maximum generalized entropy in this sort of most efficient slicing from one QES to the other, minus the generalized entropy of the larger QES. In this case, the empty QES. So this thing is the amount of post-selection required, the sort of number of qubits needed post-select on, and then the complexity is exponential on that. So plugging in that conjecture with these results, find the following curve for the complexity of decoding stuff in the interior over time. So initially, this is the complexity of decoding on either just the black hole or just the radiation. Initially, the one you can reconstruct it from is the black hole, and then the complexity of doing so grows exponentially with time. At some point, we hit the page curve, page time, and the larger of the two minimums becomes the empty surface rather than the non-empty one, the island forms, and now the interior is reconstructible from the radiation, rather than the black hole. The complexity of doing so stays the same. And then actually the exponential part stops growing. So the complexity just grows linearly with time for a little bit. Finally, when the black hole is actually half evaporated, the sort of which sweep is more efficient changes, and the lunch starts getting smaller. And so the complexity starts going down and down and down. Eventually, when it's completely evaporated, then find that there's no lunch at all anymore, and the complexity is just proportional to the evaporation time. This, of course, makes complete sense, because now all the information is in the island. We can just reverse time, remake the black hole, and have the thing spit out. Okay. And these results, by the way, agree with the complexity of doing the sort of Grover search algorithm in a sort of random unitary time model. But on the other hand, it's actually a quadratic improvement over the sort of bound that Harlow Hayden came up with for how hard this should be. So it's actually, we can do slightly better than they thought. Which may be a reason to think maybe you can do even better than this thing, but who knows? Okay, so I really want to get on to the more recent stuff, so I'm just going to very quickly talk about these slides. So sort of everything there assumed some particular choice of Cauchy slice, but we can make everything covariant. So the sort of the minimal cut obviously becomes the minimal quantum extremal surface, or equivalently the maximin surface. The other end of the cut of the lunch, the sort of other constriction is going to be a second quantum extremal surface, pretty obviously. But what we also want is a sort of covariant definition of the maximum size of the lunch. For a tensor network, this was what you might call a minimax surface, where we minimized over the maximum size you get in some way of sweeping from one end of the lunch to the other, right? But now we need to make that covariant. We need to sort of optimize overall Cauchy slices in some way, and the definition that makes sense, and very conjectural, but it seems sensible, is that you want to maximize overall Cauchy slices of that minimax surface. So you get a maxi minimax surface. Hopefully people can add a couple more to them and make a maxi minimax surface. But that's left for future work. Okay, so it turns out that assuming everything is well behaved, this should also be a quantum extremal surface. So you actually have a set of 3 quantum extremal surfaces. You have the actual minimal quantum extremal surface, you have a big bulge surface, and then you have a second constriction surface that's sort of somewhere between the two in size. So again, I don't want to go into detail this because I have other stuff to talk about, but you can actually explicitly find the sort of bulge surfaces for each of these 2 ways of sweeping through it, and they're sort of roughly where you'd expect, and they give the same answers that we found in our very heuristic picture. Okay, so the final thing I want to talk about is, Hayden-Preskel, for example, is easy if we're allowed to act on the radiation as well. And the reason for this is that if we look at the global system of black hole plus radiation, that doesn't have a Python's lunch anymore. It's just when we split it into 2 that it happens. On the other hand, it's easy to construct states where this isn't true. So an easy one is just allow a black hole to evaporate for a bit and then just measure all the Hawking radiation. And yeah, if you do that, then it's also easy to see that it's very hard to reconstruct the interior information, because you have to use Grover search again to reverse this post selection. It's also easy to see that in this case, the state has a one-sided Python's lunch, has a, if you take a slice going into the black hole, has a narrow constriction near the horizon because it was evaporating, and then as you go deeper into the black hole, into the past. And this corresponds to the fact that there's a non-empty quantum extremal surface that's actually associated with the entire boundary, even though the boundary is in a pure state. This is what we mean covariantly by a one-sided Python's lunch. Worth noting that just the quantum focusing conjecture means that you can never create a quantum extremal surface where one didn't exist before, just by doing sort of causal bulk evolution, isolated evolution of the subregion you're talking about. And so if you start with a state with no Python's lunch, one-sided Python's lunch, then simple boundary evolution can't ever create one. This is consistent with them being very, very complex. Okay, so sorry I rushed a bit through that stuff. It's because I really wanted to talk about the more recent progress and the arguments we're making. So this
Geoff,
is really
I'll pause
fine.
just to say this is your 5-minute warning.
Okay. How much could I thought I had 50 minutes.
40
Never
plus
mind.
5.
Okay. Damn. Okay. So the claim that we're making more recent work is that Python's lunches are the only source of exponential in the complexity area CFT dictionary. Argue this in 2 steps. First is that there's a counterexample to this that you're probably thinking of, and that's not actually a counterexample. You're wrong. And the second is to come up with a general procedure for reconstructing anything that's not in the lunch. Okay, just by using sort of HKLL style causal bulk dynamics. Causal bulk dynamics should be simple from the boundary point of view, and say that this is an argument that anything not in the lunch can't be exponentially complicated. Okay, so let's first do this example where there's seemingly no lunch, but they have exponential complexity. It's very simple. Just take a non-evaporating black hole, evolve it for more than the scrambling time, and then consider an interior partner of a Hawking mode. Okay, so this is meant to be very complex, but there's no Python's lunch because we just made this by unitary evolution from the vacuum state or whatever, formed a black hole from collapse. So is this a counterexample? The answer is no. The reason it's not a counterexample is that if we're going to talk about bulk reconstruction, then we can't just consider a sort of single bulk state. You need to talk about a code subspace, and you need to consider arbitrary states in that code subspace. At the very least, this code subspace needs to actually allow this interior mode to be in multiple different states. Otherwise, we can't talk about applying an operator to it or staying within the code subspace. Okay, so we've got to allow states where this interior mode is disentangled from its Hawking partner. And then we can argue that there actually will be a Python's lunch. And the way we do that is just to consider a sphere that's sort of in the past and just inside the horizon. And you can argue that once we've disentangled this mode, then the sort of quantum expansion in both of this sphere in both the forwards outwards direction and past outwards direction is negative. Okay, so if you sort of move it outwards in any direction, you decrease the generalized entropy. Then what we do is we just do quantum maximin on slices anchored on this surface. When you do that, you can argue that the maximin surface can't end up on this surface and can't end up on light-like separated from it because of the negative expansions. And so you have to get that this maximin surface is a quantum extremal surface that's sort of outside this yellow surface. That's enough to make the interior be inside the lunch, interior mode be inside the lunch, and we can explain the exponential complexity with the lunch. And actually, the answers for the size of the lunch, the exponential complexity, it depends on the size of the subspace and agrees with sort of toy model results. Okay, so that's why you shouldn't believe counterexample, but that's not enough to argue for the general result. So there's a couple of things we need to do first. The first is that we want to show that everything outside some sort of outermost quantum extremal surface can be easily reconstructed by causal bulk evolution. Okay, and the first potential problem is it's not clear that this is even well defined. You might imagine that there's instead two sort of time-like separated or partially time-like separated extremal surfaces, and there's no single outermost one that can define the edge of the Python's lunge. So we prove this can't happen by contradiction. The first thing is you consider the intersection of the two wedges associated with these extremal surfaces. You argue, so this is always either contained in one of the two extremal surfaces, or it's like light-like separated from both, the surface that bounds this intersection wedge. You can then argue that its expansions, outwards expansions are non-positive everywhere, and that's enough to argue using restricted maximum again that there's some new quantum extremal surface that's outside that intersection, and so outside both our original QESs. Okay, so this contradiction with there being no outermost quantum extremal surface that's outside both of them, and so we have a well-defined outermost quantum extremal surface. So this gives a well-defined simple thing we call the simple wedge, which is the thing we hope can be reconstructed causally. Okay, so I apologize that I'm just rushing through stuff very fast. I thought I had more time to do. Okay,
you can take like a couple more minutes just to get through it.
Yep. I've got like 2 slides left.
That's fine. Yeah, go ahead.
Okay, so it's pretty easy to see just from the quantum focusing conjecture that this wedge bounded by this non-minimal quantum extremal surface has to contain the causal wedge, right? So we have focusing along these light rays. They can't make it out to the boundary. They have to be outside the causal wedge. However, in general, there will be a gap between these two things. The causal wedge will be bounded by a surface with positive expansions, and the two will not coincide. Of course, everything in the causal wedge we know how to reconstruct pretty simply using HKLL. So the sort of question is what about the stuff in the gap between the simple wedge and the causal wedge? Can we reconstruct that? Well, the first thing to note is that the sort of definition of the causal wedge is teleological. It doesn't just depend on the state at some time t, it depends on the whole boundary conditions you use for the time evolution, right? Because that defines the event horizon, hence the causal surface. So let's say, for example, there was some matter that bounced off the boundary, came out of the white hole, bounced off the boundary, and falls into the black hole. What we can do is we can change the boundary conditions so that this matter comes out here and instead just gets absorbed at the boundary. Okay, we can just change the boundary conditions of the field so that there's no reflection that comes back in. What does this do? Well, it the matter no longer falls in, there's no longer as much focusing, more stuff makes it out to the boundary. We made the causal wedge a bit bigger. Okay, so it's certainly not the case that you can only get the causal wedge by causal reconstruction. But in general, whatever boundary conditions we choose as we sort of evolve forwards in time, we can't get all the way to the boundary of the simple wedge because we won't be able to get past the sort of outermost apparent horizon on this past causal boundary. Okay, because that will in general be outside the outermost quantum extremal surface, and we won't be able to get past it. However, what you could hope to do is first evolve forwards in time, get out to that outermost apparent horizon, get to very forwards in time, and then start evolving backwards in time with different boundary conditions. So we evolve backwards in time with different boundary conditions that absorb this shock that then was going into the past horizon. So we absorb that, and then that will make the past horizon get bigger. And then we can hope to sort of gradually iterate, stretching out each time, out and out and out, and eventually converge all the way to the simple wedge. In fact, there's situations where this is really quite easy to prove that it's possible. And the simplest one of all is just to consider a sort of chiral classical field theory in 2D, just a free massless wave equation. And then the only sources of focusing come from matter falling across. You can just remove that matter with your boundary conditions very easily and just hop from a apparent horizon to apparent horizon. And eventually you have to converge to this outermost quantum extremal surface. sort of the great vision of the project that we're trying to make work, and we think we're very, very close to, but we're still sorting out stuff, is to argue that something similar is true for arbitrary states in sort of classical GR with arbitrary matter fields and stuff, assuming standard energy conditions. And this is very hard. It gets incredibly messy. You've got you're trying to deal with the constraint equations and so on. But basically our strategy is to show that whenever the causal surface has a positive expansion, we can do a tiny little perturbation to the boundary conditions that will basically make that causal horizon be slightly tight rather than being small. If we've made the causal horizon time-like, we must have made we must have made the causal wedge bigger, and so we've expanded the causal wedge, and then we can evolve backwards in time with different boundary conditions, expand it in the other direction, and we can keep making it bigger and bigger, and the only thing that can stop us is reaching this outermost quantum extremal surface. So we have a general procedure for doing this perturbation, way of constructing it, that seems to work pretty generally. We're trying to rule out like possible weird situations where you could have problems show up and like the procedure breaks down and stuff, but we're pretty hopeful about making it work. Okay, so just to sort of summarize the whole talk, I'm really over time, so I think I'll just show all these things. Really just a summary of everything I've said. We've argued that Python's lunches give exponential complexity based on intuition from tensor networks. Ongoing work, we have arguments that even in the sort of examples of exponential complexity where there doesn't seem to be a lunch, actually secretly there is. And then we're also trying to argue that anything not in lunch can be reconstructed causally and hence simply. And we have an iterative procedure for doing that, but it's still, we're still trying to nail down the proof to the exact details as rigorously as we can. So yeah, awesome. Sorry, I second part of the talk was a bit rushed.
It'll just foster more discussion later. So I'm going to ask everyone to unmute themselves so we can thank Geoff for a very clear and great talk. Okay. Oops. Sorry, I accidentally unmuted you, Geoff. Okay, so we had a question from Alexei Malenkin in the chat. I'll just read it out. Changing the boundary conditions may send a positive energy shockwave inside the black hole. Is this a potential problem? And this is referring to your previous slide.
Yeah, good. So you certainly have to worry about that. I want to emphasize that we're not turning on sort of absorbing boundary conditions that absorb sort of anything that's sent out there. We're using the fact that we know what the state is. It's just a single fixed state we're trying to make this work for. And so we can just like manually absorb it. You could we're like sending in another shock that precisely cancels out the first shock. So this I think is something you can do without sending in a positive energy shock. I'd also say we're mostly working at the moment with just the classical case for this construction and not worrying too much about the quantum case. There was a paper by Arvin, Adam Levine, and Ronak that came out a while ago that actually argued for when there's a perturbative gap for particularly simple cases where you have a perturbative gap between the classical extremal surface and the quantum one, then there's a sort of simple bulk operator that will expand the classical extremal surface, the causal wedge out from the classical extremal surface out to the quantum extremal surface. So it seems like the quantum version should be possible too, and there's similarities with our classical approach. But honestly, for the completely general case, the classical version is like hard enough. It's like really messy and horrible and ugly, and things you would think are just trivially easy to prove, like removing energy falling in makes the causal wedge bigger, ends up very nasty and in the weeds of GR. So yeah, we're just thinking about the classical version for that particular thing at the moment.
Okay, next up is Daniel.
Hi, Geoff. So this operation, so if I understand what you kind of want to do is you want to have a boundary condition that just kind of vacuums up any particles which otherwise were going to fall across the causal horizon, which sounds to me a bit like Maxwell's demon. And in particular, as you know, it's often hard to come up with a unitary operator that lowers the energy. And now I know you can just say, oh, the initial state is fixed and so on, but actually you want to have a code subspace, right? So to have the reconstruct, like you said, right? So the initial state isn't completely fixed. So it sounds like kind of you're saying, at least within the code subspace, you want to have a Maxwell's demon. And I'm not totally sure. I mean, maybe it's okay. I don't know. It just sounds a little bit, problematic to me.
I don't think it's like
you can have states of superpositions, and maybe it'll come out, and maybe it won't. And
yeah, so good. I think okay. Let me respond to there's a few questions. One is, I think there's cases. Say you have a superposition of a state where there's not a extremal surface and one where there is, not a QES and one there is. For as in the I think in that case, like the state of the mixture, the QES will be even further out. But I think we should also think that sort of the mixture doesn't really have one well-defined QES. If it's just a mixture of like 50-50 mixture of two things where like the QES are in totally different places, or like one just doesn't have one and one does. And so I think these notions aren't going to be super precise there, but I would still hope to be able to make it all the way out to the sort of outermost QES of anything in the mixture. You'll just potentially be able to get a bit more than that, or like with some probability get more than that. I don't think we can talk about this more offline, but I don't think just morally, I don't think we're asking for anything unreasonable or too Maxwell's steamy. But I think it's a legitimate question. I think that the issue of when you have entanglement and everything's quantum and so on, and trying to come up with similar procedures for that seems really hard to argue genuinely. I think that this perturbative version is good evidence that like something along those lines makes sense. But I would be happy to make the classical version work, and that would really do for me. That at least gets you a fair bit of the way of making an argument.
Thanks.
Sebastian seems to have disappeared. He said I was going to ask a question after Daniel, so I'll guess.
Please go ahead. Somehow I'm the host. I'll take over until he connects again. Go ahead, Mike.
So my question was, in various situations in ADS CFT, I think you can manipulate the inside of the lunch by adding some operator or source at some past Euclidean time, and so one can understand sort of if you can reverse Euclidean time evolution.
Exactly.
Seems to be a way to do that. Is that directly related to the idea that you have this exponential complexity? Is it sort of known that doing the Euclidean time evolution,
like reversing the Euclidean time evolution is undoing post selection, right? It's undoing a non-unitary process. We definitely like it's very consistent, the fact that you can create things inside the lunch by having inserted them earlier in Euclidean time.
Okay.
Right. It's just like the fact that you can create stuff inside the lunch with it's very similar to my version of you evolve a black hole, let it evaporate for a while, and then measure all the Hawking radiation you collected. Right. That's a non-unitary process that prepared the state and could easily change what was inside the lunch. But once you've done that process, to undo it and change stuff inside the lunch is hard because it wasn't unitary.
Good. Okay. Thanks.
Next question is by Henry. Go ahead, Henry.
Yeah, thanks for the nice talk, Geoff. I'm just wondering if this is also an answer to a very closely related question I've been thinking about recently, which is when does a reconstruction depend sensitively on the member of the ensemble, or when does it involve wormholes, or possibly if you've got a single dual, when do you need to know about strings of brains and stuff? Is this
that's something I've thought about. I think the answer is that if it's inside the lunch, then it will depend on the member of the ensemble. in an ensemble theory. Yeah, I think they're the same thing, but I haven't thought about that hard. So yeah, I think it's a very good question.
Is there possibly some connection to say, if you try and do a pets map type construction you did in your paper in last year, whether you need wormholes?
Yeah, exactly. Well, it's not necessarily it's not necessarily like wormholes, but it's whether you need sort of weirder topologies that I think could treat as like morally wormholes, like you know, just reconstructing something in the middle of a bulk from like two boundary regions, right, where it's in the center between them, behind a quantum extremal surface. Like the topologies for the pets map that do that won't be wormholes, because they're but I think you could still argue that, yeah, that's an interesting one actually. Yeah, in that case, then it's really just a vacuum state, so we should think that there is ensemble can't affect it. So yeah, I think maybe for global reconstructions, I should think about this harder rather than giving a global answer. I think if for global reconstructions, if it's in the lunch, then yeah, maybe I'll just like abort that claim that they're the same thing, because I haven't thought about it as hard as I thought I maybe had, and we can talk about that afterwards. But there definitely feels like potential connection. I think it's a very interesting question.
We'll light up a conversation in the future. Thanks.
Yeah, exactly. Yep.
My computer revived, so I can go back to moderating. Let's have Raghu, which will probably be the last question.
I just have a quick question about this left moving versus right moving issue that you raised in the beginning. So do you distinguish between left moving stuff and right moving stuff inside the lunch? One is easy, the other is hard.
So yeah, good. So no, everything in the lunch is in the lunch. So one thing that's true is that a left moving thing, if my code subspace only concludes the left moving thing and not any of the right movers, then there just isn't a lunch. And so I can easily reconstruct it. What is true is that if I work in a code subspace where the interior mode is disentangled, the interior partner mode is disentangled from the Hawking radiation, and then I try to reconstruct a infalling mode more than a scrambling time in the past, that will then be inside the lunch. And so the claim is that it's very complex to reconstruct. And the reason for this is that yeah, if the interior mode is disentangled from its Hawking partner, then I can't just evolve backwards in time and have the thing more than a scrambling time in the past come out, because you have the back reaction, and so it will still get hidden behind the causal horizon. So it's completely consistent.
You're saying there are states in the code subspace where even the left moving guy is hard to reconstruct.
Exactly. Yeah. Yeah, and the complexity is only exponential in the size of the code subspace, it turns out. Like, even though people often think about it as really complex, if you only want to reconstruct one qubit, it's actually not that hard. The complexity is like proportional to the time the black hole has been there for, just using a group search style thing. So yeah, you need to actually make it really hard, you need a large number of modes that you've disentangled, like a big code subspace.
Okay, thanks.
Okay, I think that's all the time we have, or all the questions we have time for. Let me direct any further questions to the Slack channel, and let me ask the participants to mute themselves one more time, just so we can thank Geoff again for the great talk.
Thanks, Phil.
Okay, so now Geoff, if you want to unshare your screen.